All right, so problem number one. It says you have, turn the light on, 315 centimeters cubed of gas. Remember, you also have to know that a centimeter cubed is exactly the same as a milliliter. All right, of gas is compressed at constant temperature to 0.0457 centimeters cubed or milliliters. Under a pressure of 2.51 kilopascal. 2.5. If you need to convert kilopascals into something else, that conversion will be given. If you think you need to do that here, you do not. All right, it just says calculate the pressure initial or at constant temperature. All right, and so we have a constant temperature, and that means that you have Boyle's law. All right, so P1 V1 is equal to P2 V2, or pressure initial volume initial is equal to pressure final volume final. And as long as you remember that the units have to be the same, it doesn't make any difference what the units are. They just have to be the same. They just have to be the same. All right, so you can leave this as centimeters cubed. You can convert it to liters. You can convert it to anything you want. But whatever you convert this one to, you have to convert the other one to. That is just a waste of time. All right, so pressure one, the initial pressure, that's the question. Calculate the initial pressure. All right, and so volume one, the first volume was 315 centimeters cubed. Pressure two was given at 2.51 kilopascals. And your volume two was given at 0.0457 centimeters cubed. And so you simply divide both sides by 315 centimeters cubed, and you have your answer. So this is a very simple question. 315 centimeters cubed. They cancel. You have your answer. It didn't ask for a certain pressure. It just says, what is the pressure? And so you push the buttons and your answer is going to be given in kilopascals. All right, and you got 3 sig figs, 3 sig figs, 3 sig figs, and your answer will be given to 3 sig figs. And when you push the buttons, you get 3.64 times 10 to the minus 4. Kilopascals. And again, if there was some another problem that said convert that to atmospheres, that conversion factor has to be given to you. The only conversion factor that you have to know for pressure, well, you have to know that what you do have to know is a millimeter of mercury is the same as a torr. So if you see torr, that's a millimeter of mercury. And then 760 millimeters of mercury is 1 atmosphere. So you must know that. That's a perfect conversion. Will not determine the number of sig figs in the question. All right, question number 2. It tells you that 39.5 centimeters cubed of helium. 39.5 centimeters cubed helium. Again, same as a milliliter. Centimeter cubed, same as a milliliter. At 18 degrees Celsius. And 106 kilopascals. Was cooled, right, until 7.7. So now we're going to cool it until 7.7 centimeters cubed of helium was at a pressure of 106 kilopascals. Calculate the temperature. All right, and so we'll do calculate the temperature, and we're going to have that in degrees Celsius. All right, so what you have to notice is if they give you the same pressure, then you're at constant pressure. They can tell you it's at constant pressure, or they can list that exact same pressure 2 times. So this is constant pressure. If it's not changing, it is constant. All right, so when you have constant pressure, you have Charles's law. Which is a V1 over T1 is equal to V2 over T2. Again, your volumes, they just have to have the same units. And this is the reason why people will miss it. Because the question will ask for the answer in Celsius, and so people will leave the temperatures in Celsius. T can never be Celsius. Delta T, you can use Celsiuses to get your delta T, but if it is T, it must be in Kelvin. If there is a multiple choice and you put Celsius in there, that answer is there. It is the wrong answer. If you put Celsius there, you will get the wrong answer, whether it's multiple choice or not. Never put Celsius where you have a T. It is always wrong. All right, so again, but the volume, they have the same units. We are set. And so you have your 39.5 centimeters cubed. And your temperature, so you have 273.15 plus 18. You have a 291.15. All right, and so you have no decimals, 2 decimals. You give your answer to no decimals, 291 Kelvin. All right, and then volume 2, 7.7 centimeters cubed. And you're looking for your T. All right, and then you have to practice this. You have to be able to solve for this. Some people are not very good at math. If it is multiple choice, you're not going to get any credit. If it is not multiple choice and you set this up, but you can't solve for it, you will get some partial credit. But you need to be able to solve for T and do it correctly every time. Many ways to do it. All right, I will do it the long way. Multiply both sides by T, and so you see the T's cancel. Then we have to multiply both sides by 291. 291. When we multiply this side by 291 Kelvin, they cancel. Then I have to divide both sides by 39.5. Divide both sides by 39.5. All right, and this told you that it's going to be cool. So if you don't get a temperature less than 291, you know you did the math wrong. All right, so when you take your 7.7 and multiply by 291, and then divide by 39.5, you get a temperature of, and now we're at 2 sig figs. 7.7 is 2 sig figs, and so your temperature is 57, and that's in Kelvin. All right, so there will be a choice that gives you a 57 degrees Celsius. That is not the answer. All right, so remember, in order to get to Celsius, you take 273.15 plus your degree Celsius to get your Kelvin. All right, so we put in the 18. That's how we got the 291. So we have to subtract 273.15 from both sides. Our degree Celsius is equal to our Kelvin temperature minus 273.15. And so you take your 57, which has 0 decimals. You take your 57 and subtract your 273.15, which has 2 decimals, and you give your answer to no decimals. And the answer to this question is your temperature is equal to negative 216 degrees Celsius. So yes, it was cooled quite a bit. All right, so again, temperature is the most often missed problem. For somebody that knows exactly what they're doing, they leave the test thinking they got 100% and they got a 50% because they did not convert their temperatures to Kelvin. All right, even if you know exactly how to do the problem, if you don't have the right units, you have the wrong answer. All right, number 3. Number 3, we got 91.3 grams of oxygen. We have a volume of 8.58 liters. And we have a temperature of 21 degrees Celsius. Calculate the pressure. All right, so now we are not going from one to another. The first two was, here's your pressure and volume, what is it now? Here's your temperature and volume, what is it now? This doesn't give you a first pressure, and they ask for the pressure. All right, so when you're given a mass, a volume, and a temperature to find a pressure, you have PV is equal to nRT. All right, so your pressure is what we're looking for, volume. All right, so there's the volume, and that is the correct units, because every time you are using PV is equal to nRT, you get a 0.08206 liter atmosphere per mole Kelvin. If you ever use the wrong R for an equation, you're not given any partial credit. You must know that you're looking at the units. If you see the unit volume that has a liter and you use a joule, you're not going to get any credit. All right, so make sure you know why you're using the R value that you're using. That's liters. That has to match the units in your R value. All right, so we know we have to have liters. We do. We know we have to have atmospheres. So our answer is going to be given in atmospheres when we're done. Moles. All right, so we have grams. So we take our 91.3 grams of oxygen, and you should keep the O2 with it, so that when you write that there are 32.00 grams of O2 per mole of O2. All right, if it was O and not O2, then it would be 16. But O2, that means there are 2 oxygens. 16 times 2, 32. All right, and so this will give us our moles. Take your 91.3 and divide by 32, and you have 2.85 moles of oxygen. All right, so that's your N value. So that's N. N is moles. All right, R, we got T. Again, you put in 21, and that multiple choice question, that answer is there. That is the wrong answer. Make sure you always convert T into Kelvin. 273.15. You have 294 Kelvin. 294 Kelvin. 0 decimals, 2 decimals, 0 decimals. All right, so your pressure, when you solve for pressure, it is nRT divided by V. We get to do that again. Do not miss these because you don't know simple algebra. Divide both sides by V. All right, so you have a 2.85 moles of oxygen. You have 0.08206 liters times atmosphere per mole Kelvin, and those units are given to you in the constants page. All right, and that obviously says Kelvin, so make sure you have 294 Kelvin. Kelvin cancels Kelvin. And then your volume, also in the right units, was given to you, and that was your 8.58 liters. All right, and so the liters cancel the liters, and the moles cancel, the kelvins cancel, and you have your pressure in atmospheres. And so when you push the buttons, you got your 2.85 times 0.08206 times 294 divided by 8.58. You give your answer to 3 significant figures because there's 3, there's 4, there's 3, there's 3. 8.02 atmospheres. Again, I did not clear my calculator, so if you have a number that's different here, if you have a 1 or a 0 or whatever, that is, again, just did you keep all your numbers or did you round them? It doesn't matter. I do it all the different ways. So again, if your number is off only by the last significant figure, remember how they work. Certain digit, a digit that has some uncertainty. So if you have it wrong in the last decimal, the chances are you did it right. You just rounded numbers prior to getting your answer, which is fine. All right, number 4. Calculate D, which is density. And remember, density is mass over volume. And we are in the gas chapter. And so the mass is going to be in grams, but the volume is going to be in liters. All right, so we want the density of ammonia gas at 31 degrees Celsius and 751 millimeters of mercury. All right, so you can memorize the density equation for the gas laws, or you can derive it. Regardless, make sure you have the right units when you are finished. So PV is equal to nRT. Again, what did we just do above? We took the mass of oxygen and we divided by the molar mass of oxygen to get the moles of oxygen. And so that is a nice conversion. So for any gas to find moles, you simply take the mass and divide by the molar mass. So mass over molar mass is equal to moles. So I just do that substitution. So I have PV is equal to, instead of N, I put in my mass divided by my molar mass, because that is the same as N, and then R and T. And so now I have to solve. So once you have this down, you can solve for molar mass, you can solve for the density, lots of different things that you can solve for once you know that mass divided by molar mass is how you get moles. All right, so I know that density is mass over volume. So I have to get mass, and then I have to divide by volume. In order to get that, I divide both sides by volume. And so when I do that, I get, well, I can do that intermediate step. Pressure is equal to mass over volume, and then I have RT over the molar mass. Well, I want the density on the one side by itself, and so I have to multiply both sides by molar mass. When I do that, molar mass is gone. I have to divide both sides by RT, and then that is gone. And so now I have that my density, which is my mass over my volume, is equal to molar mass times pressure divided by R and T. So again, you either derive it, you memorize it, whichever way you want to do it. All right, so we need the mass, and you need to know that density is mass over volume. All right, so NH3, so we need the molar mass. We go to the periodic table, 14.01 for the N, 3.03 for the 3 H's, 17.04 grams per mole. You need to remember how to get the molar mass. That will never stop. We'll do molar mass every single chapter. All right, and so that is 17.04 grams per mole. You need to know the units of molar mass, grams per mole. Pressure, we just said above, the one thing that you have to memorize is how to get from millimeters of mercury to atmospheres. And so in order to do that, you got to take your 751 divided by 760 millimeters of mercury in 1 atmosphere. So you got to divide that by 760 in order to get atmospheres. So when you take 751 and divide by 760, you get a 0.988. That is a 0.988 atmospheres. Must be in atmospheres, 0.988 ATM. All right, and why does that have to be in atmospheres? Well, because the R value you're going to use is 0.08206 liter atmosphere per mole Kelvin. And so your pressure has to be in atmospheres to cancel atmospheres. All right, and then your mole in the denominator and the numerator cancels the mole in the denominator and the denominator. All right, and so again, temperature, that's the reason why most people miss this. And that is the easiest thing to get right, apparently the easiest thing to get wrong too. 273.15 plus 31 is 304. to the correct number of sig figs, Kelvin. And so divided by 304 Kelvin. And so then Kelvin cancels Kelvin. Degrees Celsius would not cancel a Kelvin. So you take your pressure times your 17.04 divided by 0.08206. And then why people will miss this is you push your divided by button again on your calculator, 304. All right, and that will give you a density of 0.675 grams per liter. So 0.675 grams per liter is the density of NH3 at that pressure and temperature. All right, if you change the pressure, you change the temperature, you will change that number. All right. So density of a gas, grams per liter, is the units for density of a gas. All right. Number 5. Vaporize the liquid at 100 degrees Celsius and 755 torr. The volume of a 0.548 grams of vapors is 237 milliliters. Calculate the molar mass. All right, so we have a temperature given, 100 degrees Celsius. We have a pressure given. Pressure is 755 torr. The volume is the question. We're given a mass. The mass is 0.548 grams of vapors. Oh, the volume is not the question, so they just tell you the volume later. So the volume is 237 milliliters. The question is calculate molar mass. All right, so they give you a temperature, a pressure, a volume, and a mass, and they want you to calculate the molar mass. And so we go right up above here where we did our little substitution. PV is equal to nRT. We substituted N for M over molar mass. We're going to do the same thing again. All right, so PV is equal to nRT. And we know that to get moles, we take the mass and divide by the molar mass. So again, we have PV is equal to the mass over the molar mass, R and T. All right, last time we wanted density, we solved for mass over volume. This time we want the molar mass, so we have to solve for molar mass. So we have to multiply both sides by molar mass because it's in the denominator here. So molar mass in the denominator cancels molar mass. So multiply both sides by molar mass, divide both sides by PV. And then you have your equation for molar mass. Molar mass is equal to MRT over PV. Now you have to have the right units. Right? So the mass units that we have to have are going to be grams because you must know that molar mass is grams per mole. And so the mass unit is grams, and that's what's given, 0.548 grams. R is always, for PV is equal to nRT, 0.08206 liter atmosphere per mole Kelvin. Temperature is always in Kelvin, so you add your 273.15 and you have 0 decimals, you have 2 decimals, you give your answer to 0 decimals. And so your temperature is 373 Kelvin. So Kelvin cancels Kelvin. All right, and then we divide that by the pressure, and that is 755 torr. Remember that a torr is the same as a millimeter of mercury. And so that means that this is 755 millimeters of mercury because a torr and a millimeter of mercury is the same. Divide that by 760 millimeters of mercury is 1 atmosphere. So when you take your 755 divided by your 760, you get 0.993 atmospheres. All right, and then you have your volume. The volume is 237 milliliters. You have to convert that to liters. You can show your work. You don't have to show your work. Do not get this wrong. This is a 0.237 liters. You can do that by changing the m to times 10 to the third, and you 10 to the minus 3, and then you have a 237 times 10 to the minus 3 liters. You can divide by 1,000 milliliters in a liter, whichever, or just move the decimal 3 spots and write it, 2.237 liters. But you need to convert that to liters. You do not have to show that work, but you need to be able to do that correctly every time. All right, then you just push the buttons on your calculator and you have the molar mass. So 0.548 times 0.08206 times 373 Kelvin divided by 0.993, and then also divided by 0.237, and now you have your molar mass. And the molar mass is to 3 sig figs, because everything but R is 3 sig figs, 71.3, and that is in grams per mole. Now, if you wrote out the entire pressure without rounding it, this very well could be a 2. All right, so again, if your number is different in the last significant figure, because that's the significant figure that has some uncertainty, you most likely did that correct. All right, so that's how you find the molar mass from PV is equal to nRT. All right, number 6. All right, we have a reaction, PCl5. It's a gas. Goes to PCl3, which is a gas, plus Cl2, which is a gas. All right, and so it's going to be clearly labeled on the test that all of these are gases. And then you have to know that instead of using moles, if you have a reaction that's all gases, you can always use moles. But if the reaction, all reactants, all products are gases, then you can use volume. You can say 1 liter of PCl5 will decompose into 1 liter of PCl3 and 1 liter of Cl2. Or 1 mole decomposes into 1 mole and 1 mole. But only when it's gases can you use a volume and a mole. All right, so here's the question. We have 10 milliliters of PCl5 at STP. All right, how much Cl2? Can be produced? At 22.5 degrees Celsius and 745 millimeters of mercury. All right, so this is a good question. So you can do this the hard way. You can do it the easy way. The hard way is you have enough information here, right here. You have enough information here to go to moles, and then you would have moles of PCl5. And then you would say that 1 mole of PCl5 would make 1 mole of Cl2. Then you use PV is equal to nRT, and then find your volume of Cl2. That would be the hard way to do it. The easy way to do it is you have 10 mils of PCl5, and we know that for every 1 mil of Cl2 formed, 1 mil of PCl5 had to decompose. Again, this is a all gas equation, and so you can use volumes and any units of volume. 1 liter of this will produce 1 liter of that. 1 mil of this will produce 1 mil of that. Whatever, 10, whatever, 1 centimeter cubed, 1 centimeter cubed, whatever volume units that you're using, they just have to be the same. 1 mil, because of the balanced chemical reaction, is a 1 here, will produce 1 mil of Cl2. And so what we have is we have 10 milliliters of Cl2 at STP. All right, what it didn't ask how much Cl2 can be produced at STP. It says how much Cl2 can be produced at 22.5 degrees Celsius and 745 millimeters of mercury. All right, and so you need to know what STP means. All right, and if you did it the hard way, you would still have to know what STP is. I like to remember 0, 1 here so I don't mess anything up. All right, 0, 1. So 0 is your temperature in Celsius, and 1 is your atmosphere. All right, so that's your temperature and your pressure. Of course, we don't want Celsius, and STP is perfect. So this is 273.15 Kelvin and 1 ATM. So what we're doing is we're taking a volume at STP, and we want to know what that volume is going to be at a different temperature and pressure. All right, and so nothing here is constant, and so the moles is constant. We're not changing, we're not taking any out or putting any in. So we have the combined gas law, P1 V1 over T1 is equal to P2 V2 over T2. So you have to use the combined gas law, pressure, volume, temperature. None of those are constant. All right, so remember that when you're using these equations, that these just have to be the same units. So you can convert them to atmospheres if you want. You can leave them, you can convert the 745 to atmospheres, or you can convert your atmospheres into millimeters of mercury. It doesn't matter. It gives you exactly the same answer. Volumes, okay, we're given milliliters. All right, so our answer will be in milliliters. And then temperature, there is no choice, must be in Kelvin. If you have T, it has to be in Kelvin. All right, so pressure, I'm going to go in millimeters of mercury, 760 millimeters of mercury, because 1 atmosphere is 760 millimeters of mercury. The volume, we had 10 mils. We had 10 mils of our Cl2 at STP. All right, and so the temperature at STP, 273.15 Kelvin. Now the question is, what is my volume now? Well, my pressure is 745 millimeters of mercury. Again, they are the same units and they will cancel. Volume, that's the question. What's my volume when I'm at this temperature and pressure? Here you have your 22.5. You must add 273.15 and you will get 295.65. So when you do the 0.65, that rounds to 0.7 because 1 decimal, 2 decimals, 1 decimal, 295.7 Kelvin. All right, so again, the pressure and the volume just have to be the same units. Temperature must be in Kelvin. All right, so we have to multiply both sides by the 295.7. And we have to divide both sides by 745 millimeters of mercury. And then you see the millimeters of mercury cancel, the Kelvin cancels, and we are left with milliliters. So we take our 295.7 times 760 times 10, and then divided by 745 and divided by 273.15. And our answer to 3 significant figures is 11.0. And so your volume is 11.0 milliliters. All right, and so our temperature increased, and so that would be an increase. When temperature increases, volume will increase. So if you have a high temperature, you will have a higher volume. All right, when your pressure decreases, all right, pressure goes down, the volume again will increase. So in both of these cases, our temperature went up by 22.5 degrees, 20, whatever it was, 22.5, yes, and our pressure went down. It went from 760 to 745. All right, and so this could be a predict the volume compared to 10 milliliters. Well, the temperature says the volume's going up, the pressure says the volume's going up. So there is a 100% chance that your volume is going to be greater than 10 milliliters. Sometimes the temperature would say volume down and pressure would say volume up, whatever, so you couldn't really predict it. But if they both predict an increase in volume, well, then you know that your answer has to be greater than the 10 milliliters of the initial temperature and pressure. All right, so that is the combined gas law to solve that problem. All right, so the next one is also a reaction, problem number 7. In this one, we have sodium bicarbonate. And to balance it, we need 2 moles. And now sodium bicarbonate is a solid, so we cannot do volumes. We have to use moles. And then that gives us sodium carbonate, Na2CO3. And it gives us carbon dioxide, gas, and water liquid. All right, now note, this is a solid. All right, so the only one that we can use PV is equal to nRT on is CO2. That is the only one that is a gas. Solids, no. Ideal gas law can only be done on gases. PV is equal to nRT, can be used for gases only, not solids, not liquids. If you had water above 100, then you could use PV is equal to nRT because then it is H2O gas. All right, so the question is, what volume of CO2 gas at 77 degrees Celsius and 756 millimeters of mercury can be produced from 26.8 grams of there's an H there, NaHCO3, sodium bicarbonate. All right, so what you have to do here is you have to get your mass and convert that into moles. All right, and so we're going to have moles of sodium bicarbonate. We want moles because we can use the mole ratio. We cannot use a volume ratio because they're not all gases. All right, and so we see that 1 mole of carbon dioxide is formed when 2 moles of sodium bicarbonate react. All right, so once we have moles of sodium bicarbonate, we can convert that to moles of CO2. All right, we have a temperature, we have a pressure, we have a gas, and so all we need to do is find the moles and then solve for the volume. All right, so we take our 26.8 grams of our sodium bicarbonate, and we have our 22.90, I think, sodium, 22.99, not 90, 22.99. Hydrogen, 1.01, carbon, 12.01, and 3 times 16. That is 48, 60, 324. That looks like it is 84.01 grams per mole. Did that a little fast. Yep. So that is the moles, but that's not moles of CO2. That is moles of your sodium bicarbonate, NaHCO3, NaHCO3, NaHCO3. That is not a gas. You cannot use that mole number in PV is equal to nRT. All right, so we have to convert it to CO2, which is a gas. All right, so we see from our balanced equation 2 moles of our NaHCO3 will react to produce 1 mole of CO2. So we take our 26.8, divide by 84.01, and then we have to divide that by 2 in order to get moles of CO2, 0.638 moles. All All right, so that is your moles of CO2, which is a gas. And now we have a temperature, which you immediately add 273.15 to 273.15, and that gives you your 0.15, which 350.15, so that is 350 Kelvin, no decimals, 2 decimals, no decimals. And then we're using PV is equal to nRT. Our pressure must be in atmospheres, so we divide by 760 millimeters of mercury is 1 atmosphere. All right, so then we have everything we need to find the volume. All right, so we have PV is equal to nRT. We want the volume, so divide both sides by P. The volume is nRT over P. Well, we just found the moles of the gas, CO2, that is a 0.638 moles. R is the 0.08206 liter atmosphere per mole Kelvin. And our temperature is 350 Kelvin. And so the Kelvin cancels the Kelvin. Again, make sure that you have Kelvin for your temperature. Anytime you have T, you have to have Kelvin. Kelvin cancels the Kelvin. Moles cancel the moles. And we see that we have to have our pressure in atmospheres. So we take our 756 millimeters of mercury, divide by 760 in order to convert it to atmospheres, 0.995. So that is our 0.995 ATM. And so your atmospheres will cancel your atmospheres, and now your answer is in liters. So you take your 0.638 times 0.08206 times 350 divided by 0.995, and that gives you 18.4 liters. So that is the volume of oxygen gas that you would prepare, that would be produced from 26.8 grams of sodium bicarbonate. All right, grams into moles, mole ratio, get your moles of your gas. PV is equal to nRT for the gas only, gas law. And that, again, Kelvin is always your temperature, and PV is equal to nRT. Atmospheres is always your pressure, and liters is always your volume, because PV is equal to nRT always uses the 0.08206 liter atmosphere per mole Kelvin. All right. Number 8. Number 8, we have 3.85 liters of carbon monoxide. 3.85 liters of carbon monoxide. And here is the key phrase, collected over water. I don't think I've ever given a test without the phrase collected over water on at least one of the problems. All right. Collected over water at 25 degrees Celsius. So we have a temperature, 25 degrees Celsius, which would be converted quickly to 298 Kelvin is the temperature we want, not in Celsius. 689 millimeters of mercury. So we have a pressure given. 689 millimeters of mercury is our pressure. All right, and so again, I showed you the equations you're going to be given and the charts you're going to be given. So what you do is you see collected over water. That means find the pressure of water, and it is all based on temperature. So you look up the pressure of water at 25. You have the table, 25, you go across, and off the table, you see that you have 23.8 millimeters of mercury at 25 degrees Celsius from the table. table number? Table 5.6 maybe, or whatever. The table that's given on the test. So whatever that table says for the pressure of water at 25 degrees Celsius, which would be 23.8, that's your pressure of water. All right. What is the question? How many grams? Oh, I don't have a... Okay, so here's the reaction that it was produced from. We got, it's like we've got formic acid, HCHO2. That is a liquid that is converting to H2O liquid and carbon monoxide gas. All right. So this is your balanced chemical reaction, and in this one, everything is 1-to-1. All right, I like the last one better where there was not a 1-to-1 ratio. So how many grams have reacted? So how many grams of HCHO2 liquid reacted? All right, so for this, to answer this question, what we need to have is moles. And so we have a volume, we have a pressure, we have a temperature. So we're going to find moles of our gas. The only gas we have is carbon monoxide. That's the gas that was collected over water. So from PV is equal to nRT, we're going to find moles of CO. Then we convert that using the mole ratio, because we can't do a volume ratio. That's a liquid, that's a liquid, that's a gas. The only time you can do volume ratios is when everything is a gas. Mole ratio from this gas to this liquid, which was the question. And once we have moles of this liquid and we have the formula, so we have the molar mass, we can convert moles into grams. All right, so this one's about a little different. It's the opposite of the other one, which we were given the mass of the reactant and we found the volume of the product. This time we're given the information on the product and we say how much of this reactant was used. All right, so the hard part here is the pressure. When you see collected over water, we have the pressure of CO, all right, is not equal to the pressure total. All right, so your pressure total is equal to the pressure of the CO plus the pressure of water. So in order to get the pressure of CO, which is what we have to have for the moles of CO, we take and we have to subtract the pressure of water from both sides. And so that is your pressure total minus the pressure of water. And so your pressure of your CO is equal to 689 millimeters of mercury, 689 minus the 23.8 that we looked up on the chart. Right? And so, but we don't want it in millimeters of mercury either, so then we have to divide that by 760 as well. All right, so our volume is correct. So the volume number, 3.85 liters. The pressure, when we take our 689 and subtract our 23.8, all right, we get 665.2. That's not the number we want, 665.2 or 665 to the correct number of sig figs. Little bar there. All right, but I don't want millimeters of mercury. I know that that has to be in atmospheres. Divide by 760 millimeters of mercury in 1 ATM. All right, and so when I divide that by 760, now I will give my answer to 3 sig figs, 0.875.